So hello everyone and welcome back to STUDIFYSUCCESS. We are back here with another amazing chapter of class 10th, which is acids, bases and salts. All the notes of this chapter are available in the description section, and for more study content you can always visit our website studifysuccess.com. So let's get started with the chapter. So we have already studied about acid, bases and salts in class 7th as well. So let's do a quick recap of everything we have studied. I have accumulated everything on this slide. So firstly we have the definition of what is an acid and a base. This definition may be new for you, so let's start with the taste. So we have studied that acids are sour in taste and bases are bitter in taste. So you don't have to taste them, but the acids are sour in taste and the bases are bitter in taste. Litmus paper. So litmus paper is a paper you can see here in this image. This is a litmus paper. So it is obtained from a plant which is called lichen. So from the plant lichen we obtain a paper which is called the litmus paper. This is a natural indicator. What do you mean by an indicator? Indicator is any substance which changes its color or which tells us that this particular sample is acidic or basic. So we have two types of litmus paper. We have a blue litmus paper, this one, and we have a red litmus paper. So whenever we dip a litmus paper into a solution, it either changes its color or it remains the same. So whenever we dip a blue litmus paper into an acid, it changes to red. Here you can see we have a blue litmus paper, we have dipped it into an acid and it has changed its color. But when we dip a blue litmus paper into a base, it does not show any reaction. So this is how we can identify that whether a sample is acidic or basic. Then the reaction with red litmus paper. You can see here we have a red litmus paper. Whenever we dip a red litmus paper into a base, it changes into blue, and with acids it does not show any reaction. So this can be a little confusing, but you can remember it that red is a sign of danger. So bases are dangerous, so they always change red litmus paper to blue. Or you can remember it the other way around as well, that acids are dangerous, so they change the blue litmus paper to red. Anyway, which is feasible for you, so in that way you can remember it. Then we have reaction with turmeric. We all know turmeric, we all use turmeric at home, and you must have seen this reaction. So if we have a turmeric stain on any of our cloth, and whenever we wash it, we see that the yellow stain changes to red orange. Why does this happen? Because the soap we use is basic in nature, and the turmeric changes from yellow to reddish orange when comes in contact with a base. So turmeric stays yellow with acids and it changes its color to reddish orange in bases. Then we have phenolphthalein. All these litmus, turmeric, phenolphthalein and methyl orange, all of them are indicators. The only difference is litmus and turmeric are natural indicators. They occur in nature, whereas phenolphthalein and methyl orange are synthetic indicators. Synthetic indicators are the one which are produced in labs by humans. They are man-made. So phenolphthalein is a colorless indicator. Normally it is colorless. With acids as well it remains colorless, but with bases it changes to pink. Similarly, methyl orange is orange in color as the name suggests. In acid it changes from orange to red, and with bases it changes to yellow. So these things, that what is the color of a certain substance with a certain indicator, all these things you should know. And now we know that acids are sour in taste and bases are bitter in taste. Another new thing by which we can define acids and bases is that whenever acids are dissolved in water or acids are in aqueous medium, in aqueous medium means they are dissolved in water, they release H positive ions. For example, we have HCl. Whenever we have HCl and we mix it with water, HCl dissolves in water and forms H positive ions and Cl negative ions. Okay, now we know for acids release H positive ions in aqueous medium. Whenever we mix an acid in an aqueous medium, it releases H positive ions. For example, here we have HCl. HCl has formed H positive and Cl negative. It breaks down. It dissociates into H positive and Cl negative ions. For bases, bases form OH negative ions, which are called hydroxide ions. Here we have NaOH. So NaOH, when mixed in water, dissociates to form Na positive ion and OH negative anion, which is hydroxide ion. So this is how we define acids, that acid release H positive ions in aqueous mediums and bases release hydroxide ions in acid mediums. So now that we have discussed about acids and bases, let's continue with some basic key terms of this chapter, which we are going to use in the chapter ahead. So firstly, we have strong acids and strong bases. We know what an acid is and we know what a base is. Acids dissociate into H positive ions and base release OH negative ion, both in aqueous medium. So strong acids are the one which release the H positive ions readily or easily in water. As soon as we mix them in water, they release H positive ions. For example, here you have HCl. HCl, as soon as it comes in contact with water, it breaks down or it dissociates into H positive and Cl negative ion. It gives out this H positive ion, which makes it an strong acid. Then we have strong bases. Strong bases release OH negative ions readily in water. So this NaOH will completely dissociate and form Na positive and OH negative ion, making it a strong base. Now we have weak acids and weak bases. Weak acids do not easily release H positive ions and weak base do not easily release OH negative ions. So here you can see we have acetic acid. Acetic acid, when breaks down, when dissociates in water, it forms acetate ion and H positive ion. But you can see here we have a double-headed arrow. This means that this reaction is reversible. Both of these ions can combine again and again form the acetic acid. It can again form this acetic acid. So the reaction is reversible. That is why we have a two-headed arrow. So this means that this acetic acid is not completely dissociated in water. Some of the acetic acid is in the form of these ions, whereas some ions have again combined to form the acetic acid. So complete dissociation is not visible in case of weak acids and similarly in case of weak bases. Weak bases, we have ammonium hydroxide as the example. Then the next term we have is concentrated acids or bases. Concentrated acids means when we have the concentration or the amount of acid in a solution is more or is greater than the amount of water. So we have a solution of acid and water. For example, we have 80% acid and 20% is water. The solution is concentrated. But if we have 40% acid and 80% is water, so the amount of water is more than the amount of acid, then the solution is said to be dilute. But how do we dilute this concentrated acids? So concentrated acids cannot be directly diluted by simply adding water as we have added air. Acids are very corrosive, so when we have to dilute the concentrated acids, we cannot directly add water to the acids because this reaction between water and acid is highly exothermic. Exothermic means they release large amount of heat is released in this process. So this reaction is highly exothermic and the temperature increases rapidly, as you can see here. Due to this high temperature and large amount of heat, the acid can splash over us and it can cause burns. So the correct way to dilute an acid is to add the acid into the required amount of water drop-wise with constant stirring of the solution. So addition of acid to water is the correct method to dilute any acid rather than addition of water to acid, The reason is because the reaction is highly exothermic, and if we add water to the acid, large amount of heat is produced and the acid can splash over us and cause burns. The next very important key term and a very important topic is indicators. We already know some basic things about indicators, so let us quickly review it. So indicator is a substance which tells us basically that is if a sample is acidic or basic. It tells us the nature of the substance. Now we have various types of indicators. We have natural indicators, we have synthetic indicators, and we have olfactory indicators. You must have heard about natural and synthetic, but olfactory is new for you. So natural and synthetic indicators are the one which change color to show that if a substance is acidic or basic. But olfactory indicators change their odor or their smell, or they produce some kind of a different odor with acids and with bases. So with smell they tell us that this is an acid and this is a base, whereas natural and synthetic indicators use colors to indicate the nature of a substance. Now we have two examples of each here which you should know. Litmus, as I told you, is obtained from lichen plant and it comes in two colors, which is blue and red. We have litmus solutions as well and we have litmus paper as well. So blue litmus changes into red in acids and red litmus changes into blue in bases. Turmeric, again a natural indicator, it stays yellow with acids, but with bases it changes to reddish orangish color. Then we have synthetic indicators. Phenolphthalein is a colorless indicator. In acids it remains colorless, but with bases it changes its color to pink. Methyl orange is orange in color. With acids it becomes red, but with bases it changes to yellow. Then coming to olfactory indicators, we have onion and vanilla essence. We know onion and vanilla essence have a characteristic smell. So with acids, onion retains their characteristic smell, but with bases the smell vanishes. And same for vanilla essence as well. With acids, the smell which is characteristic and unique to vanilla essence stays, but with bases the smell vanishes. In this way, all these substances indicate whether a substance is acidic or basic in nature. I have also provided the definition for olfactory indicators. They are some substances whose odor changes in acidic or basic media, indicating the nature of the sample. So this is all about indicators. So now we are done with the basic introduction and basic definitions, basic terms. We can start with the chemical properties of acids and bases and how they react with different substances. So we have various chemical reactions of acids and bases. The first chemical reaction is the reaction of acids and bases with metals. This we have already studied in metals and non-metals as well. So acid and bases, when react with metals, they produce a salt and hydrogen gas. Base as well, when they react with a metal, they produce the respective salt and hydrogen gas is liberated. We have examples. We have HCl reacting with zinc, giving us zinc chloride and hydrogen gas. We have NaOH, which is sodium hydroxide, reacting with zinc again, giving us sodium zincate, which is a solid and it settles at the bottom, and hydrogen gas. So here you can see hydrogen gas is liberated, and the liberated hydrogen gas, how do we check that the liberated gas is hydrogen gas? So we have this apparatus. We use a delivering tube to deliver the gas in this soap water solution. We can see the bubbles of hydrogen gas coming. Then we bring a burning candle or a burning matchstick near to this solution, and we see that the candle starts burning with a pop sound. So this is a characteristic test to check for the presence of hydrogen gas. To bring a burning candle, if it burns with a pop sound, that indicates that the hydrogen gas is being liberated in the following reaction. So here a very interesting question can come from this topic only, which is that why curd or any other source substance is not kept in brass or any other metallic vessel. Brass is a metal and curd has acetic acid. Other source substances also have acids in it. So all these substances contain acids, and we know that we have seen that acids react with metals to give us salt. So the reaction will produce salt, which may be toxic or which may be poisonous, and hydrogen gas is also liberated, which can degrade or spoil the food item. That is why we do not keep curd or any other sour substance in metallic vessels, because they can spoil the food due to the liberation of hydrogen gas. Then the next reaction which we have here is the reaction of metal carbonates and metal hydrogen carbonates with acids and bases. Metal carbonates is simply a metal X with carbonate, which is CO3, and metal hydrogen carbonate is again metal X with carbonate and hydrogen in between. So metal carbonate and metal hydrogen carbonate. Simply when again metal carbonate or metal hydrogen carbonate, when both of them react with any acid, they form a salt, carbon dioxide and water, because here we have carbonate. So carbon dioxide is liberated and water is also formed. Okay, so we have some examples here. We have sodium carbonate and we have HCl. So acid here used is HCl, and we have carbonate. So it is giving us sodium chloride, which is a salt. We have water produced and we have carbon dioxide. Coming to hydrogen carbonates, we have sodium hydrogen carbonate reacting again with HCl, which is a strong acid, giving us sodium chloride, water and carbon dioxide. So these are the reactions of metal carbonate and metal hydrogen carbonate with acids. With bases, both of them do not react with bases. So all these things you need to memorize. Again, now in this example or in this reaction, hydrogen gas is not being released. We have carbon dioxide gas which is being released. So how do we check that which gas is being liberated? Again, we have a detection test. For carbon dioxide, we had the burning matchstick or burning candle test. For hydrogen gas, we had the burning candle test. For carbon dioxide, we have the lime water test. So whenever we pass this carbon dioxide, again we have a delivery tube. We are passing this carbon dioxide in this solution of calcium hydroxide. Calcium hydroxide is basically lime water. Whenever we pass it in lime water, we see that this lime water turns milky. Why does it turn milky? Because we have calcium carbonate forming up, which is white in color, and that precipitate, due to that precipitate, we see the white milky appearance of this calcium carbonate. So the reaction is that calcium hydroxide, which is present in lime water, when reacts with carbon dioxide, it produces calcium carbonate, which is a white substance, white PPT, white precipitate, due to which we see a milky appearance of the lime water, and we have water. When we had excess of carbon dioxide, when we pass it, the milkiness disappears because of the formation of calcium hydrogen carbonate. Okay, so we need to make sure that excess is also not being passed. After passing some amount of carbon dioxide, we see milkiness in lime water. This is the characteristic detection test for carbon dioxide. So moving ahead with the next reaction, which is reaction of acids and bases with each other. So we have seen three reactions. We have seen reaction of metals with acids and bases. We have seen reaction of acids with metal carbonates and metal hydrogen carbonates. Then we are seeing reaction of acids and bases with each other. We know that when acid and base react with each other, they neutralize each other's effect, and the reaction is termed as a neutralization reaction. We already know about this. So a neutralization is a reaction between an acid and a base, which gives us salt and water. So what is basically happened? We have an acid and a base, acid has H positive ions and the base has OH negative ions. This is definite. Except from this, we have some remaining components. These remaining components join together to form the salt. So now, as the remaining parts have joined, we are left with hydrogen ion and hydroxide ion. Both of them combine to form water. So this is the complete mechanism which goes behind the neutralization reaction. It is the reaction of an acid with a base which gives us salt and water. We have a very popular example of sodium hydroxide reacting with HCl to give us sodium chloride and water. We often see neutralization reactions in our everyday life as well, and we have studied this in earlier classes. So we know when a wasp or any bee stings us, their venom is basic in nature. So wasp sting is basic in nature, whereas the sting of a bee is or an ant is acidic in nature. So we apply the opposite to neutralize it. We apply vinegar to neutralize the sting of a wasp, which is acidic in nature. Then we have acidity or gastric problems we suffer because of the excess of hydrochloric acid in our stomach. So we take antacids or antacids which have sodium bicarbonate acid. So milk of magnesia is a popular example for this. We take magnesium hydroxide, which is present in milk of magnesia, to neutralize the excess of hydrochloric acid which is present in the stomach. The next reaction which we have is the reaction of metallic oxides with acids. So first of all, metallic oxides are the oxides of metals, which we have studied in metals and non-metals as well. They are the oxides of metals, and we know that they are basic in nature. How do we know that? We made a solution of metallic oxides and we checked it with indicators. So by that we know that they are basic in nature. So we also call them basic oxides. So hence, because they are basic oxides, they do not react with base. Base and base do not react. So bases do not react with metallic oxides. Why? Because metallic oxides are basic in nature. So metallic oxides or basic oxides react with acid, similar in a manner like bases react with acids, and again like neutralization reaction, they produce salt and water. Okay, here we have an example of copper oxide reacting with HCl, giving us copper chloride and water. We see a blue-green complex. You can see the image also here. So metallic oxides are basic in nature. They react with acids to give us salt and water in a similar way like neutralization reaction. The next we have the reaction of non-metallic oxides with base. Now we know that metallic oxides are basic. So non-metallic oxides are acidic in nature. They are the oxides of non-metals. Metallic oxides are basic and the oxides of non-metals are acidic. So hence they are acidic, they do not react with acids, but they do react with base, again in a similar manner like neutralization reaction, and they give us salt and water. We have carbon dioxide here, which is a non-metal oxide. Carbon is a non-metal and we have carbon dioxide, which is a non-metallic oxide. It is reacting with the base, which is calcium hydroxide. Calcium hydroxide is a weak base. It is reacting with calcium hydroxide to give us calcium carbonate and water. Again we have salt and water. So these were all the reactions of metals and non-metals with acids and bases. So now we have studied about acids and bases. We also know about the key basic terms of acids and bases and the chemical reactions of acids and bases. Now we are going to study pH. So in order to check the strength of an acid or a base, we have developed a pH scale. A pH scale is used to measure the hydrogen ion concentration. It gives us the concentration of hydrogen ion, by which we can calculate the strength of a solution. Okay, so the P in pH refers to potens, which is a German word which means power. So it gives us the power of hydrogen or the hydrogen ion concentration. So on a pH paper, we apply a universal indicator which gives us or which tells us that whether a substance is acidic or basic in nature. So it gives us different colors for different concentrations of hydrogen ion concentrations. Now for a pH paper, we must know three basic values. A pH scale has 14 divisions in it. It starts from 0 and it goes on till 14. 7 is the midpoint of a pH paper and 7 represents neutrality. If any sample or any solution has pH 7, it means that the solution is neither acidic nor is basic, it is neutral. If the pH is less than 7, then all the substances of this range are acidic. If the pH is more than 7, then all the substances are basic in nature. So, as we move towards the right, the basic nature keeps on increasing. So, if I have a sample A here, which has for example 9 as the pH, and if I have a sample here which has 14 or 13 as the pH, the sample B with 13 pH is more basic. So, as we move towards right, basicity increases, basic nature increases. And similarly, as we move towards the left, the acidic nature increases. If I have a sample over here which has a pH of 3, so the acidic nature as compared to a sample with 0 or 1 acidic nature will be lesser. So a sample with pH 1 will be more acidic than a sample with pH 3, and a sample with pH 13 or 14 will be more basic than a sample at pH 9. So I hope this is clear that firstly 0 to 14 there are 14 divisions in a pH paper. 7 is the midpoint, which represents that a sample is neutral or a solution is neutral. Towards the left, all substances are acidic in nature and acidic nature keeps on increasing. Towards the right, all the substances are basic in nature and the basic nature keeps on increasing. Solutions with pH more than 7 are basic, with less than 7 are acidic in nature. So this is what a pH scale represents. Now we have some basic everyday applications of pH, and here you can also see a pH paper, and here various examples are given. Let us have a look at them. So we have pure water and blood in the center which has 7.4 pH, so it is neutral, okay, because 7 represents neutrality, so this pure blood and water are neutral. Milk of magnesia, you can see it has 10 pH and sodium hydroxide has 14 pH. Now both milk of magnesia and sodium hydroxide have pH greater than 7. This means that they are basic in nature. Now if we compare both of them, out of both of them, sodium hydroxide is more basic than milk of magnesia. Why? Because as we keep moving towards right, the basicity increases. So sodium hydroxide is more basic than milk of magnesia. Now let us come towards the acids. We have lemon juice and we have gastric juice. Both of them has pH less than 7. Less than 7 pH, both are acids. Now which one is a stronger acid and which one is a weaker acid? Gastric acid, which has 1.2 pH, is a stronger acid than lemon juice which has 2.2 pH. Why? Because as we keep moving towards the left, the pH or the acidity keeps on increasing. Now we have some everyday applications that we see where pH is used. So our body works in a narrow range of pH 7 to 7.8. You can see that our body works in a neutral pH. So all over the body the pH is approximately neutral, 7 to 7.8. Acid rains. Acid rains, as the name suggests, they are acidic in nature. This means that their pH is less than 7. So they have pH 5.6 or less than 5.6. Such rains are called acid rains. The same acidic water comes to the rivers, and this water is unfit for the survival of the aquatic life in the rivers. Why? Because they have very low pH, which is 5.6 or even less than 5.6. Then we have indigestion. What happens during indigestion? There is excess of acid, excess of hydrochloric acid produced in our stomach, which causes pain and irritation. This we have seen this example. So to get rid of this pain, we use antacids like milk of magnesia, which has magnesium hydroxide, and you have seen the pH is 14. So it neutralizes. Again, the neutralization reaction comes into action during this indigestion example. Then we have tooth decay. So what actually happens during tooth decay? Let's see that first. So when we eat food, we have various bacteria in our mouth, and various food particles get stuck in our teeth. So that bacteria degrades the food particles and forms acids out of them. Okay, it produces acids from the sugar particles and from the food particles that we eat. Now these acids degrade the enamel. Enamel is the outermost layer of the teeth. It is made of calcium hydroxyapatite, which is the hardest substance found in the body. So enamel gets degraded due to the action of these acids. Now due to this, the pH is very low in the mouth, and at this low pH the tooth starts getting decayed. So tooth is decaying at this low pH, which is lesser than 5.5. So using toothpaste, which is basic in nature, to remove all these bacteria can neutralize the excess acid, as well as they will remove the bacteria and they will remove the food that is stuck in our teeth, preventing tooth decay. Then we have many animals. As I have told you, we have wasp, we have bees, which have acidic substances in their sting, which causes pain and irritation. We use mild bases like baking soda on the stung area, which gives us relief. Stinging hair of nettle leaves, inject methanoic acid. Methanoic acid is an acid which causes burning pain. We again apply some base on it to neutralize the effect. So this was all about pH and its application, which we often see in daily life. So this was all for part 1. We have covered the basic definitions, basic key terms of acids and bases. We have covered the chemical reactions of acids and bases, and we have covered pH. In the next part, we will cover salts and various examples and applications of the salts. So thank you so much for being with me in this video. Stay tuned for the second part. You can access the notes of this chapter in the description section, and for more study content you can always visit our website studifysuccess.com. Thank you so much.